As introduced in the previous segment, we will be majorly talking about acceleration of particles, and we will start with one-dimensional motion of a particle, and in this segment whatever we are going to discuss, almost everything is known to you, should be known to you from your 12th standard discussions. Okay, but still this you can take it as a recap of what you have already learned. Now, I will be talking about some visualization aspects, so that later on whenever required we can use these things, okay, because the concepts as such are known to you, that I assume. And so to start with, suppose we have a graph between, say, the displacement and I will say so the position coordinate of a particle. A particle is moving on a line, maybe, so it is a rectilinear motion. So there is a line and a particle is moving on that, okay. It is free to move either side, either ways, but it cannot go beyond these things, it cannot move away from that line. So it is a rectilinear motion and a particle is moving on that line, and S is the position coordinate on that particular line. And then if we draw the curve between this position and time, then what happens is, and all of you know that the slope at any point, if you think of a triangle like this, okay, so this is nothing but ds over dt, and that will give you the velocity. So whenever we look at any curve or graph, so we should think in terms of the slopes and the area under those curves. So these basically always will have some physical meaning attached to them. Like for example here, it gives you the velocity of the particle, right? So because that means if you choose two, so this is dt within a small patch of time, very small patch of time, and the movement that the particle has made is ds. So ds over dt will give you the velocity, and from here you can always write that, say, ds is nothing but v dt, and then if you integrate, so you will get the curve, you know, distance travelled s2 minus s1 is nothing but v dt. That means if I have a curve which is between, say, v and t, so you are plotting v versus time, then and in that curve, if you have something, sorry, I will draw with a different color maybe. So if you have v versus t like that, then the area under this curve, so because this is nothing but the area under this vt curve, v versus t curve, so if you suppose between, sorry, say between some time t1 to some other time, say t2, if you take the area, so then you will get s2 minus s1. So you can simply write that s2 minus s1 is nothing but integration of v dt. Okay. Now but then again, so this was about the area. Now you can also talk about the slope here, again the same thing, and this slope is nothing but dv upon dt, which is nothing but the acceleration. Okay. So the area under the vt curve gives us how much it has moved on the line, and the slope gives us the acceleration. Now from here we can write that dv is nothing but a dt, and again if you integrate, that means this integration we are doing so that we can talk about the area under the curve, which again will reflect here. Okay, I'll just suppose I draw A versus T now, and suppose suppose you have a curve like that. Now we are not sticking ourselves to a constant constant acceleration motion which you are comfortable with. I am assuming that, so that v is equal to u plus at, that formula you always used. S is equal to ut plus half at square, and v square is equal to u square plus 2as. So these three formulas you have been using quite a lot, and the crux in those formula is constant acceleration. As soon as the constancy of acceleration is removed, you can't use those formulas. Okay. Now, so if such a thing represents the acceleration versus time, then the area under that. So, for example, suppose I take between any time t1, any time t2. Okay. So the area under that curve will give us the change in velocity. So v2 minus v1, okay, will be that area under the curve. So these are the three basic curves which are very important to always have feeling about. But then there are two more curves which are also important, and they are like these. Say one is, suppose you have a curve which is between acceleration and the position coordinate s. Okay. Now under that case, what would be what can you infer from the area? See here, in the previous here we wrote that A is dv by dt, right? So if you have, say, A is dv upon dt, which I don't like this, dv over dt, which you can always write as dv over ds times ds over dt, which is nothing but v times dv over ds. Or you can write that from there you can write that A ds is nothing but v dv. Okay. So that means now if you integrate this, so that is why we are trying to draw this, that is A versus s. If you write or draw and then pick any s1 and s2. So the area under that curve will give you which is nothing but, say, v square v2 square minus v1 square half. So this basically will tell you that kinetic energy gain per unit mass. So the area under the A versus S curve gives you the kinetic energy gain in moving from S1 to S2 per unit mass. So this is one more curve which is of importance. And the last curve which I wanted to discuss was, suppose you have a curve which is V versus S now. Okay. Now you have a curve, say, which something looks like that, and suppose you have again at a given point, say you have, this is dv by ds, right? So dv over ds. So this is the slope which represents dv over ds. Now if you draw a perpendicular from that point, and let this line, the perpendicular, meet the s axis at say this point, and you drop a perpendicular like this. Now these triangles, say I would say name them as say ABC. So this triangle ABC is similar to this. So if I said dV by ds here and 1 here, okay, so that means these two triangles are similar, and then what I can do is say CB over AC, okay, which is nothing but CB over V. So this is the velocity, right? Is nothing but dV over ds over 1, so which is nothing but dV over ds. Fine. So which tells me that CB is nothing but V dV over ds. Now what was V dV over ds? That was nothing but our acceleration, right? So that means if you draw a V versus S curve, then this distance here will give you the acceleration of the particle. So these are some curves which are useful for getting the accelerations or getting the kinetic energy change when you do not have functional representation of acceleration or velocity or something. You can only plot the experimental data. Now if you can plot experimental data of A versus S or V versus S, so from there directly at every location you can calculate what was the acceleration by doing these drawing these curves. So that's the idea about these 5 curves. So I would request you to be quite comfortable with all these 5 diagrams, and they will be quite helpful. Okay. And then so these are all in one dimensional, and as introduced in the previous segment, next segment we will go into 2-dimensional motions, and we will see how to deal with them. See you in the next segment.